As I've said, my name is Matthew McKnight. I'm a technical specialist here at Autodesk. I work from our Melbourne office, and I support our manufacturing customers across the region, across Australia and New Zealand, who are using or looking to adopt our technology. Today's presentation is on Millie's prosthetic and how we used Fusion 360 to break down the traditional barriers of the design and manufacturing workflow. And a little bit of background, because some of you may not actually know what or who Millie is. Millie is a greyhound. Here's a photo of her as a pup. So it's actually one of the most adorable photos I've seen in a long time. Little Millie, only a few months old. And she was rescued from, well, she's a greyhound rescued from the racing industry, who was adopted by two loving owners, Ed and Nora, and when they adopted her when she was only a few months old. Now Ed, just out of circumstances, is an architect who uses Autodesk solutions, and that's how really we became in contact with Ed. And further to that a little bit later in the webinar. Now Millie at the time of adoption already had an amputation. The reasons surrounding that were unknown though. It wasn't exactly clear why she'd actually had part of her left front leg amputated, just up from her paw. Now this is, if we fast forward to 2016, this is Millie around the age that I came to know her. And by this stage she's a reasonably developed greyhound. She's almost fully grown for the better part. But she'd had numerous procedures since, moving into Ed and Nora's family to try and improve her comfort and ability to be able to use her leg. Also during that period, Ed and Nora had gone about the process of acquiring a number of different prosthetics to help Millie to be able to move around, in particular when she's out of the house, when she's outdoors, to be able to go down the park or go for walks and those sorts of things, and to make life more comfortable and give her additional freedoms that she wouldn't otherwise have if she was just solely reliant on her front right leg. Having said that, though they provide a lot of freedoms for her, the typical process of getting a prosthetic has a number of challenges associated with it. And realistically what we were looking to do is to try and break down some of those challenges, and that's really why Ed approached us. And he was looking for, or looking to improve on the experience associated with getting a prosthetic and using that prosthetic with Millie. Now, to give you a little bit of an idea on the project timeline, Ed actually approached one of our business partners, and I'll allude to that a little bit later on. And but from that conversation, there was a kick-off meeting that took place with a number of different parties involved, including Ed and ourselves at Autodesk. If we fast forward about 12 to 18 months, more recently, which is towards the end of last year, the project was actually highlighted at Autodesk AU in Sydney, where we showcased what we'd been able to achieve through this project. Now, if we look at all of the steps that it took to get from point A to point B, there was a reasonable process associated with it. In the first instance, what we did is Millie had a scan, or effectively an impression of her leg, cast into a plaster cast. And using that cast, we were able to then scan that and bring that information into a CAD environment. From here, we reverse engineered Millie's front left leg so that we had a reasonably accurate representation of what her existing leg looked like. From there, we then moved into a concept design stage where we started playing with some ideas about how the prosthetic would mount to her leg and the foot, how it would work, and the cover system and so forth. But at this stage, it was a really generic design, because at this point in time, neither Ed nor myself or many of the others involved in the project had much experience in designing prosthetics, let alone a prosthetic for a greyhound. So really what we were doing was trying to investigate numerous different ideas and concepts at this stage as a means of trying to validate whether we could actually achieve the project. From here we then moved through to a much more detailed but still a prototype design, where we're able to come up with the shape of the prosthetic, but a lot of the features and functions that were required of that prosthetic, and include those as a prototype that then Ed and Millie were then putting through vigorous testing to ensure that it met the design objectives. Now from that, there was a number of outcomes that took place, a number of requirements around changes to the design. As an example, it was realised at about this stage that Millie, who loves to get out in the water, out in the sea, that the prosthetic would fill full of water. So what we needed to do was implement a drain hole for the water to be able to escape the prosthetic to make it comfortable for her to wear. So, from this prototype stage, there was a number of things like this that we realised that we needed to change about the design, but they were more incremental designs rather than radical changes to the overall design. And this then led to the final design, which was then effectively the same design that was showcased at Autodesk AU in October, November last year. Now, for many of you who don't know what Autodesk AU is, it's their regional events that are run around the globe. Most people know of Autodesk AU, which is held in Las Vegas, but there are also regional events that attract large audiences. As an example, AU Las Vegas attracts somewhere in the region of around 8 to 10,000 attendees. In Australia, it's around sort of the 700 to 1,000 attendees. Nonetheless, we got an opportunity to highlight this project at Autodesk AU in Sydney this year, and both Millie and Ed were up on stage showing the progress that we'd made and a little bit of their path, and talk through some of the challenges that we're able to overcome as part of that. So that was really good. Further to that, and at the same time, Ed and Millie are also showcased on a large number of media around not only Australia but the world. So at the event, they recorded segments for the likes of 7 News and Today Tonight. She also made a visit in the following days and weeks to the likes of 7 Sunrise, and she was also highlighted in online editorials like The West Australian, 3dprint.com, Daily Mail and Huffington Post. So there was a lot of media around this, and it's because there are a lot of challenges for people like Ed who have a pet that has an amputation or a challenge, physical challenge, that could be helped through the use of the technology that we're trying to showcase. So we've looked at the result. Let's have a go back to sort of the beginning and talk a little bit about the kickoff meeting and some of the objectives that we outlined at the start of the project. And you can see here, these are some of the initial designs that Ed brought to the table in a lot of the discussions around where he wanted the next generation of design to head. If we look at what came from this, you can actually see, and we can discuss these relative to previous experiences. Firstly, it was about fit. We needed to ensure that the next generation of prosthetic was specifically made to suit Millie, not just any greyhound or any other animal. Realistically, that is one of the biggest challenges, is getting a prosthetic that is specifically made for your pet, your animal. Next, what we wanted to do was to look at the way that the prosthetic could be maintained. And you can look on the right, and though a lot of these prosthetics are well made, the challenge is what happens when I need to replace, say, the foot or a component of the design. Often that requires the prosthetic to be sent back to the manufacturer for refurbishment and then returned, some period of time afterwards. So we were, one of the key objectives was the ability to be able to maintain the prosthetic throughout its life. Another critical aspect was the weight, and this was around the adoption and also the performance. If it was too heavy, it's unlikely that Millie's going to adopt something that she has to, that's difficult for her to maneuver and move around. But also performance, we wanted to give her the flexibility and the freedom to be able to run in this prosthetic, not just be limited to walking around. Furthermore, we wanted to be able to adjust it and fine-tune it. So rather than having fixed lengths or a fixed fit to a leg, how can we adjust a lot of these parameters? And also it had to be easy to use. How can it be quickly attached to and detached from Millie's leg. And we also had some project objectives. From a design perspective, we wanted to look at, whether it was possible for almost anyone to be able to do a similar type of thing with limited training. We also looked at manufacturability. Though we have a vast array of manufacturing capabilities at Autodesk, the reality is that most people that are in this situation wouldn't necessarily have ready access to those types of things. So is it possible to make a prosthetic using a consumer-grade 3D printer? When it came to purchasing components, where possible, we actually wanted to be able to purchase off-the-shelf items rather than custom making absolutely everything. We also wanted to try and minimize the cost as well. Now, we didn't want to compromise quality in doing this, but we definitely wanted to try and keep the cost down where possible. So let's have a look at some of this, really the critical parts of the process. I'm not going to go through everything step by step. We'd be here for quite some time if I explained it all. But what I'm going to do is try and capture as much of the critical part of that process for you so you can understand a lot of that timeline. Firstly, it came to leg casting. Now, I was unfortunate that I didn't actually have a photo, and I wasn't able to get a copy of the photo in time for this to show the casting that was made of Millie's leg. But it's in many respects is very similar to the casting that you would get if you had a similar procedure where you had a break or possibly a dislocation, and then you needed a cast put on your arm or leg. The reality is, in this instance, it was a very thin casting though. So the material was very thin, that the plaster that was actually used to set the casting was very thin as well. Now, the good thing about this process is that it was a general procedure. It was completed by a vet, so it was completed by Millie and Ed's local vet as part of another procedure. I think she was getting some vaccinations done at the time, and so what they did is they got them to do the casting as part of that visit to the vet. The good thing about this is minimal stress to the animal. It's unlikely that the animal, potentially needs to be sedated during this process. They can be awake. You can comfort them. It's very, it's a very minimal intrusion on the animal in terms of getting the dimensions that you need to be able to make an accurate representation of, in this case, Millie's leg. It was fairly accurate and an easy process as well. For such a low stress procedure, it is generally, considered probably one of the better ways, and in hindsight, looking at all of the different options that we had, probably one of the better ways of getting the information that we need to the level of accuracy that we needed as well. The other thing is fast turnaround. It didn't take long for us to be able to do this. Literally the same day the casting is available for us to be able to use. In this instance, with Ed in Sydney and myself and the scanning equipment that we used located in Melbourne, we did have to get it posted down, but literally it really does open up the door for people that are working in a collaborative effort like this to be able to share that information of those castings across multiple locations. And that's really what it comes down to is, the ability to be able to share this information. So it doesn't necessarily mean that Millie and I necessarily need to be in the same location. We can be in different locations and I can get an accurate representation of what Millie's leg looks like. And finally, it was relatively low cost. Now, when I reached out to Ed to understand what that cost was, he wasn't entirely sure, but in the scheme of things, we don't expect that it would have been much more than around $50 to get that casting. So as such, it's generally a reasonably low cost part of the project. So now that we had this casting, this plaster casting of Millie's leg, what did we do with it? Now, it was shipped to us at Autodesk, and it came as a thin casting which had a cut down one side of it, which had been used to remove the casting from her leg. And what we did is we actually cut the casting into two pieces and then used a laser scanner to scan that. Here you can actually see images that were taken recently. We don't have any of the procedure because at the time we didn't think to take any. But this is the same piece of equipment that was used in the same process. You can see here that the scan is actually happening on a little plastic container. So it's effectively an arm with a laser scanner head on it. You engage with the trigger and point the laser scanner at the object, which gradually gains information, locations, points and data relative to the geometry. And it brings that into the software that is then used to export out to us a mesh file that is representative of the geometry. And that's effectively what we did. The process is very quick and easy. And if I look through and go through a number of the reasons, we'll see, firstly, accuracy. We get very, very accurate results in relation to the casting. So it's all related to the dimensions of the, whatever it is that you're scanning. In this case, we were scanning the casting. But the dimensions are, very, very accurate. We're actually talking sub-millimeter accuracy on an item like this. Fast turnaround was another key to this. We were able to scan the geometry in less than an hour and have that ready to then process through a CAD system. So the turnaround on going from the casting to data that we can start working with inside of our design was very, very quick and easy. For us, it was low cost. Now, this is going to be an argument, and I've got a follow-up slide to give you some, some other ideas that you might be able to use here. The point to make here is that we already had the equipment available to us, so it was a low cost to get that scan done. The reality is, for most people, however, that would be trying to replicate this, they're not going to have access to, or may not have access to, a similar type of equipment that we did here. I will look at that a little bit further to investigate a number of different ways that you can potentially replicate a similar workflow. The great thing is that once we've got this scan data, which comes in the form of a mesh file, an STL file, we're able to then bring that information into the CAD application and work with it in either Fusion 360 or Inventor. And I chose Fusion 360 for a number of reasons, and we'll go into that, but Fusion 360 actually has a dedicated mesh environment. Before I highlight how you can use that, in this first instance here you can actually see the mesh that's been imported into Fusion 360, and you'll notice that there's a lot of triangles that make up the mesh. You'll notice that it's not necessarily clean. There's holes in it, there is rough edges, and this comes from, one, the process of scanning it, but two, the nature of the product that you're actually scanning, because we were scanning a very rough piece of fabric that was being held together by this plaster. It didn't necessarily lend itself well to coming out perfectly like you might get with, say, a plastic component that's a molded component that you might scan. So there was some challenges that we had in working with the scan data. Really, it just came down to cleaning up the data so that we had a reasonably accurate representation of what the casting looked like. What happens if you didn't have a laser scanner like we did? Okay, one, you can outsource it. Potentially, there's the opportunity of trying to find someone in your region or someone possibly even outside of your region if you can post the castings to them. That can do this. Now, obviously, if you're paying a consulting service, you will have to pay for this. Hopefully, because it is such a simple process, it shouldn't cost much, but it's definitely going to cost more than what it cost us, which was really just the time to use the equipment. The great thing here is the fact that you're going to get a very accurate result. The scan information is going to be very close to the original casting that will have been done of the leg. You could potentially even look at photogrammetry, and for those of you who don't really understand what photogrammetry is, here's a very short sort of video of what that process looks like. You can place an object, so potentially you could place something like the casting onto a still a pedestal, and then move around it taking a series of photographs that can be uploaded into technology, and Autodesk have technology called Recap that enables you to convert those photographs into a 3D model. Now, we didn't look at this because we had the laser scanner. It wasn't something that we looked at, but I think that you'd still get reasonable results out of using this type of technology. The good thing is that the cost would be reasonably low as well. The barrier to entry into using this type of technology is very low in terms of cost, and really it would then just cut back to the cost of the casting to get that done. Now, the argument is, could you use this to do the same with, say, Millie's leg? The challenge with doing that is, how do you keep Millie still to ensure that the geometry is not changing whilst you take those 20, 30, 50 photos? And that really poses the challenge. And in many respects, I think it would be very, very difficult to be able to use this. In that instance, you might be better off actually using hand measurements, whether that's hand measurements of the leg itself or hand measurements of the casting. Potentially, that might provide a better way. Another way would actually be to potentially look at sectioning or cutting the casting carefully, try not to adjust its dimensions, into numerous sections, tracing the profile of the leg and then scanning that into the geometry and then using a lofted surface to do it. So there's a number of different potential ways that you could replicate that could be low cost and get you reasonable results. Okay, so now that we've got the scan done of the plaster cast, where did we go from there? Well, then we moved through to reverse engineering that scan data into a format that we could then work with inside of Fusion 360. So it was really about converting the scan data to a CAD format. Now again, this was all done directly inside of Fusion 360. The reason being is that Fusion 360 has a dedicated mesh environment. This enables you to easily and quickly clean up the scans. It can help you convert scans, or there's workflows and being able to convert scan data potentially to elements that can then be used for freeform surfacing manipulation. There you can leverage a range of different tools to manipulate the geometry of the part. But it also comes with equally strong capabilities to be able to use traditional, or what I call hard surfacing techniques, where we use things like lofted curves and splines. And that's really, in highlighting my workflow that I used here, there was a number of different ways, and potentially everyone that's watching this webinar might look and think, well, why didn't he do it this way or that way? It really comes down to personal preference, and in many respects, that is some of the power that Fusion 360 gives you, is the freedom and flexibility to be able to use whatever you think is appropriate. Now, I predominantly used hard surfacing techniques to generate the profile of Millie's leg, predominantly because I come from an old school CAD background. I learned 10, 15 years ago surfacing techniques that were highly reliant on splines, lofts, sweeps, all of those trimming surface type technologies. What this meant is that I was able to take the scan data that we'd imported into Fusion 360, inserted numerous planes along the length of the leg. You can see them there. I created intersection curves between the plane and the scan data. I created splines that enclosed the section through each of those sketches, and then lofted between each of those to create a lofted surface. So it was one nice clean surface. And then what I did is I used freeform surfacing technologies where appropriate to either, one, close out the surfaces. One of the most challenging parts was actually at the base of the leg, where you've got an enclosed surface there coming together from various different sides. And the other challenge was adjusting that surface to ensure that it really did replicate as closely as possible the scan geometry that came in. So this is a quick look at what that workflow looks like. So here we've got the scan data that's been brought in. I've simply placed a plane that aligns along the leg but doesn't intersect with the geometry. Now I use that plane as the basis of creating every other plane. I just simply offset that plane numerous times. Now I'm going to work through one example and then we'll replicate that numerous instances. So we offset a plane, in this case an arbitrary figure. I've used 50 mil, In the actual file I used 10 mil, so I had a lot of accuracy up the length of the leg, which had a lot of change. I can create a mesh section which creates a curve on a plane where the plane intersects the mesh geometry, and you can see there that it creates a series of curves, or a single curve if it was one complete surface, that I can now use as the basis of my profile for Millie's leg. Now, because there is so much change in here, predominantly because of the fabric that's used as part of the plastic cast, what I chose to do was to insert a spline that reasonably closely approximates the dimensions and shape of the profile of Millie's leg that we got from that casting. So moving around the shape of the intersection, I would place spline points on that curve or close to that curve, and then enclose a volume. Now once you've done that, you can see that it doesn't necessarily perfectly align, so we can move around and adjust those. I can grab the points, and I can adjust the strength of the curve, or the strength of and influence of that curve. I can potentially even delete them if necessary. The idea is to try and have as few as you want, but in Millie's leg, there was so much change through the course of the length of her leg, it wouldn't necessarily make much of an influence in the outcome that we have here. And you're better off actually having something that contours or closely replicates her leg rather than something that's beautiful and smooth. So once we've done that, we effectively did that numerous times up the length of her leg, higher than where we expected the prosthetic to end. And then using all of those curves, I simply created a lofted surface that moved between all of those sketch entities. And then that created one nice clean surface that we could then use for the basis for effectively everything that we did from here. Now, the one thing you'll notice is that we have an open end on the bottom of the foot. It's partly because there was very limited information that we had there. So what we did is we used some of the freeform tools to create a very organic and as close as we could possibly get representation of what we thought the end of Millie's leg looked like. And then we stitched all of this together as a freeform surface, and we were using that as the basis of the design. Now, if we compare this back against the scan data, you will notice a couple of things. One, you'll notice that in about a half of the design, it very closely follows the contour of the scan information you can have. You can see the mesh there, which is the casting that we'd scanned, and the brown sort of leather looking texture of the surface that we used to represent her leg. On the other side, which is the side that's shown here, it's not closely representing. And that is because when they put the casting on Millie's leg, they put a little plastic strip down her leg so that when they cut the casting off of her leg, the blade that they use to cut, or the scissors that they use, has very little chance of actually penetrating through and actually cutting Millie's leg. So there was a little plastic profile that stretched up the entire length of her leg. Now, in the profiles that I used, what I did is I created a representation of what that profile looked like, and I tried to predict potentially where Millie's leg would go within reason. So you'll see that there is a difference between one side, which very accurately represents Millie's leg, and the other side, which is more of an interpretation based on the geometry and information that we had at hand. Having said that, as a result of this, it was very accurate. The results that we got with, in working with this data and this workflow, and the feedback from Ed and what he could gain from Millie, was that this, like none of the previous prosthetics, fit her better than what she did previously experience. So let's have a look at some of the other components that were critical. The foot design. The foot design had a number of criteria, and so if we relate this back to the objectives of the project, you'll notice that fit, it needed to be comfortable. In terms of maintenance, it needed to be replaceable. This is a component that actually wears out. weight. It needed to be lightweight, so that it wasn't all of a sudden this mass, a heavy mass at the end of the prosthetic. It was uncomfortable for it to use or difficult to use. And adjustment, we wanted to give some degree of adjustment so that we could compensate for a lot of the unknowns in the system. We wanted it also to be easy to use and simple to work with. Now, in our concept design, we were only really focused on the fit of the prosthetic to Millie's leg. And in some ways, what we were trying to do is to gauge the height. So in doing that, what we actually designed is we designed a very, very simple prosthetic using the geometry that I showed you prior, which was all this surface that we created that represented her leg. We simply offset that. We offset an allowance for foam that we would use between the plastic of the prosthetic and the outside of Millie's leg. And then we offset the thickness of the plastic and then simply create a round sphere at the base at the height that we thought was appropriate based on the dimensions that we took. And then we created some geometry to bridge between those. And that's really as simple as that first iteration was. Now, the idea was never really to have a fixed foot on this design. And from here, we then moved, when we started moving in the prototype design, which had a lot more detail, we started investigating various different formats for the foot. We used a simple ball that had a thread on it. The thread meant that we could move the ball up and down to adjust the height. And being spherical, it meant that it was reasonably, easy for it to move around using. And it was easy to manufacture as well. We also looked at some other alternatives. You can see here was one of them as well, to give some flex. So one of the things we realized by having, a hard, non-compliant component on the end of the prosthetic was that it really had no give. There was no cushioning. So if Millie was running on, say, a hard surface like concrete, the impact transferring back up the prosthetic could be quite harsh. So we looked at, are there ways that we can design a foot that has some flexibility and give? Now, the reality is it came with its own unique challenges in that if you try and print something like this, the print part actually has, strength in certain directions, and predicting accurately how this is going to react was really quite challenging. It actually led to a failure of a prototype of this. And as such, what we did is we moved away from trying to make the foot to one of the other objectives, and that was to try and procure as many of the components as we possibly could. So what we did is we actually ended up buying an off-the-shelf rubber foot that is typically used in machine to be mounted onto a piece of equipment or machinery that you find in an industrial site. But the good thing here is you can see that it screws onto a fastener, and this is just a M10 standard fastener that is bonded into the underside of Millie's prosthetic. And then it's locked in place using a washer. Now, in this instance, we printed a washer, but you could have just as likely gone and bought an M10 nut that could have worked in this instance in much the same way or fashion. Now, how did Fusion enable us to find this? Well, the good thing is if you go inside of Fusion, you'll notice that there's a link in here to insert Master Car component. Now, Master Car for Australian and New Zealand customers may not be familiar, but it's an industrial supplies company. So from directly inside of Fusion, I can do a search for things like rubber feet. I can narrow it down visually by choosing, things from their catalog. But I can also use the filters on the left-hand side to filter down for the specifics that I'm needing, because there are potentially thousands of different variables here. So I can choose a metric thread, I can choose the diameter that I want, I can choose the mating thread, I can even choose the hardness, whether I want a hard or soft. Now it's narrowed it down to this, rubber foot, which I can then interrogate, look at the specifications, I can look at the drawings, can understand the potential that it's going to work for me. And by saving this in a step format, it will automatically import this into a Fusion 360, where I can work with this CAD data to then further investigate the likelihood that it's going to meet our requirements. Now, the good thing is a lot of this, it brings in a lot of the information that's necessary for us. So if I go through and cut a section of the design, you'll actually see that it not only has the rubber outside that's critical to us, we want that nice and compliant, flexible to take the impact, but it also has the threaded insert, which is a steel insert that we can then use to screw onto the fastener and engage with the lock nut to hold it tightly in place. And that's effectively what we did, is we were able to find this rubber, what's called a polyurethane rubber bumper, which was reasonably low cost at around $15 US each. That was strong enough, comes with a steel core in a thread that we could access, but also compliant enough. This has actually got a durometer of 40A, which is quite soft, which meant that it was really good for Millie, who's often running on hard surfaces, one, because it removes some of the shock of the prosthetic hitting the ground, but two, it also adds grip. So when she's running on something that might be slightly slippery, especially when you try and run a plastic on, say, concrete, those two materials have a very low coefficient of friction, whereas this rubber and the same material actually has a very high coefficient of friction. So it worked exceptionally well, to the point that Ed, I believe, has actually procured a whole bunch more of these in anticipation that Millie is going to wear through occasionally these, and they can simply be replaced by an off-the-shelf item. Okay, what about virtual testing? Because this was, again, another critical part of the workflow. Now, here you'll actually see some footage taken by Ed and Nora of them playing with Millie. Really, this was, the physical testing of the component. It was, once we'd 3D printed a component and we got the item shipped to Ed, and he'd assembled them and mounted them to Millie, and then walked it down the park and done some testing. But the reality is that we didn't necessarily want to have to do this. We realized that there was going to be a need to do this, that it wasn't avoidable, but we wanted to try and avoid every time us investigating an idea or a new concept, avoid the necessity to actually, print parts, ship them off, assemble them, mount them, and go down and try and see whether they work. This was to try and, one, cut down the cost, also two, cut down that time frame. So what we did is we started to use a lot of virtual testing as part of that workflow. This, in my eyes, helped increase the quality of the design, the overall quality. We knew before we printed the housing that the thickness of the material should be sufficient to support the needs of Millie, based on the assumptions that we'd made. Now, we were able to test a lot of this prior to manufacture or production. And this helped us reduce, one, the number of prototypes and compact the time frame in which we could do the project, but two, to lower the overall cost of the project. So if every time we were testing a new idea or concept and we had to get it manufactured and shipped and assembled and then do all the testing, potentially that was going to be costing us hundreds of dollars. So if we can try and minimize that where possible, then that was going to save us a considerable amount of time and money. We also believe that this helped improve the performance through lowering the weight of the part, because we could add weight where it was necessary but remove weight where it wasn't. Improve the strength in much the same way. Where we realized that the part might be weak, we could add some strength and stiffness to it. But then we could also investigate ideas. And that was like the example, the foot. The reality was that we could quickly and easily investigate numerous different ideas and understand what the impact might be on their design. If we have a quick look at what that workflow looks like, an example in this instance might be the fact that we want to understand, just doing a simple pinch test or compression test on the cover, to understand the impact of maybe over-tightening or tightening the straps that secure the front cover onto the prosthetic. Now, the good thing is that inside of Fusion 360, we have the ability to be able to do a lot of that virtual simulation. We simply switch into a new environment, so we're not switching CAD. It'll bring across the model and any materials that were previously assigned to it, but we can go and investigate other ideas. So maybe instead of using carbon fiber, which was originally specified, we can look at using a material like an ABS plastic that we can print. We can fix the component in space. So in this instance, I'm using the Fusion logo just to mount, to hold the position of this item. we'll then apply a few loads. Now this loads can be based off of information that you know at hand or estimates. In this case, I did a little bit of research to try and understand, well, what's the likelihood, of us being able to apply a certain amount of pressure, and then made some assumptions around that and sort of said, okay, 5 newtons on each side might be a relative sort of value or figure for the amount of compression that we might endure. Actually, I believe that it's potentially going to be higher than that, but in this instance, we were able to quickly and easily ascertain what a 5 Newton load on either side of either location is going to impart. We can adjust the mesh, so we can adjust the mesh density and the quality of the mesh. We can generate that mesh, and I did cut out a small section of this recording just to save a little bit of time in today's presentation. But we can then ascertain quickly, like visually checking the mesh or doing a mesh quality check, to understand the likelihood of whether the mesh is reasonable in terms of the information that we're trying to gather from running a simulation on this design. And once we've got that information back, we can then solve the mesh. Now we've got 2 options inside of Fusion. You can either solve on the cloud, which just frees up your computer to keep on working and allows you to run multiple analysis at the same time, or we can solve locally. Now, considering I was just producing this for today's presentation, I did a quick analysis locally, which took about sort of 3 or 4 minutes to run. So I've cut out some of that time associated with the solving of the geometry, and we should now be almost ready to have a look at the results. Now it'll bring back a whole bunch of results around safety factors and stress and deflection or deformation. Excuse me. And you can read through and look at and find the information that's critical for you. So it mightn't be that the stress is an overly critical component as long as it doesn't exceed a certain limit, but the deflection might be critical because you want to ensure that those parts engage or can stay engaged under the specific load that they might encounter. Excuse me. The other good thing you can quite quickly and easily animate these results, so you can have a look and understand whether you expect it to react in the way that the results are showing. And a lot of this information can be gathered together and inserted into a report that's automatically generated by Fusion 360 for future references or for archiving or the likes. So again, Fusion really did offer us a bunch of ways that we could virtually test the design long before we moved to production. Furthermore, if we talk a little bit about production, we actually use 3D printing, as we discussed early on. We really wanted to enable as many people to be able to access the technology or this type of workflow using readily available technology as possible. And really one aspect that was key to that was the ability for people to potentially be able to print their own parts at home, either during that design process or potentially after the process has ended, and really what they're doing is either just manufacturing or remanufacturing components as replacements for existing ones. Now you can see here that we're actually printing one of the locking nuts for the foot, and one of the early designs of the foot, just to actually, in this instance, it was a component that we were using whilst we were testing some of the other parts. The good thing is it doesn't take very long to print one of these. You can see actually by the window in the background, it hasn't taken less than a day to print those components. They clean up reasonably quickly, and they're effectively ready to use almost directly from the printer themselves. Some of the benefits that I saw as a result of using this, and you can see here that the parts here that were shown in the video, they're actually manufactured through this process, were done using an Ultimaker printer. But the flexibility, effectively we could have prints done in less than 24 hours, and that was critical because in the instance that you have a part failure, or you get a part that's lost, or you want to be able to quickly try a different version of a design, you can potentially have parts made overnight and shipped to you the following day, or used that same day if you're printing in the same location. This really did promote the ability to be able to do rapid experimentation for us, and respond quickly to the needs of Ed and Millie during that process. The cost, to give you an idea, if you were to do the printing yourself, it's really just the cost of the material and a little bit of power to run the machine. In looking at costs to outsource this, now we were using a consultant that was providing the parts to us. His estimates were around $120 per set of prints to manufacture and clean up the parts so that they were ready to be used. The reality is that though an Ultimaker is a few $1,000s to be able to acquire a product of that quality, you can get more entry-level 3D printers, and I believe that you can get them sort of starting around $400. The reality is this a very similar workflow could have been replicated using any of the FDL or most of the FDM type of printers and get fairly similar types of results. A little bit of background, these types of printers can produce a really wide array of materials, and the good thing about the Ultimaker I liked was the fact that it's got what's called a dual extrusion capability, where it can extrude two materials through the same print process. One, this meant that if you were just really using one material in the part, potentially you can print another material in the support structure that can be washed away or dissolves in an immersion bath. Potentially you can also print multiple materials. So towards the end of the project, and this is something we'll look at doing down the track, is the final design that we tested actually had a foam liner that was the comforting layer between Millie and the plastic prosthetic. The reality is we actually believe that there's a potential to be able to print that insert or liner as a soft, pliable, sort of rubberish material at the same time as potentially the outside structure. So again, these types of machines, though more expensive, give the ability to be able to do more complex prints, cutting out potentially other parts of the process that you mightn't be able to do using a cheaper machine. Just to give you a bit of background on the materials that we used, we experimented with a number of different materials, and really we didn't have too many problems, but ultimately we settled on a CPE, which is a copolyester. It's got really good chemical resistance, excellent toughness, excellent dimensional stability. The adhesion between the layers is very good. It doesn't have very high ultrafine particle count or volatile compounds. It's great for prototypes and really good for functional parts as well. Towards the end, we're actually working with a CPE Plus as well, which is a high temperature resistant variant of CPE, also has increased impact strength. The reality is that either of these materials would have been fine to print the parts, and arguably there's a wide range of other materials that would have been just as suitable. Let's have a quick look at what the workflow of going from a part to a 3D printer looks like. Now inside of Fusion you can actually outsource or ask for quotes from a number of different services from directly inside of Fusion, some that aren't available here in Australia. Though having said that, if you can or do have access to a printer or you can send the files to someone, you can just go to the 3D print dialog box and start preparing the geometry yourself. In this case, you can see here we can, inside of Fusion, get an understanding of what the poly count on the exported file is actually going to look like, so we can make educated decisions before we send the parts off and then find out when they return they're not to the level of detail that we were hoping for. So here what we can do is we can adjust the quality of the mesh that's being generated inside of the system, inside of Fusion, and create it as part of that process. Now the other thing is we can fine-tune a lot of that as well. So we can adjust the sliders if need be to get the type of finish that we're after in our design. At the end of the day, we can send this to either the program that we are then going to use to slice the part up and then print it, or we can export to an STL file, which is effectively what we did here. We exported to an STL file, and then Steve at Reality 3D Printing, which is the company that was printing the parts for us, would then go and segment or slice the parts up and then process for printing. Collaboration was another key aspect to this workflow. If we look here, you'll notice that we're all working from various different locations. Ed, Nora and Millie were all located in Sydney. We had the team at A2K, who was supporting the project and brought the project to Autodesk, are based out of Brisbane. We had myself and some other team members from Autodesk located in Melbourne and subsequent office in the Kilsyth. We even had Ali, which is another Autodesk team member help me out with some of the freeform surfacing workflows, who was working from Jakarta. And if you look at this, and least I not forget Steve from Reality 3D Printing, who was then printing the parts in Toowoomba. The reality is we're all communicating through various different channels in various different ways. And the good thing about using Fusion 360 is it really does lend itself well to this type of workflow. So if we look at the keys to collaboration, firstly, accessibility. We're able to access our data from essentially any device at almost any time. So it really didn't matter where we were or what we were trying to use, what type of product machine or hardware we were trying to use, we could access our information. We could do things like in-app messaging and sharing of files. We could do even real-time review if it was necessary. And we were all working from a common data set that was managing the revision control of our project automatically for us. Now, if I wanted to, inside of the program, I can comment and ask for people's feedback, and they would be notified that there's a request for information. And I can then further share that information. So let's have a quick look at what that workflow looks like. So again, inside of Fusion, I've got the comments panel where I can type what I want. I can add a still image. I can reference part of the model or a point of the model, and then ask for information for specific people that have been invited to this project. Now, inside of the data panel, you'll notice under the revision icon of the geometry or the design, you'll notice that I can look at the various different versions and go all the way back to initial release, look at what it uses, where it's used, any drawings that are associated with it as well. And I can even open the design that's being synced with Fusion Team that enables me to access the models even when I don't have access to Fusion 360. So you can see here that I can come into a web browser. This is just Chrome. This is running through. I don't have any software installed on, or I don't need to have any software installed on my local machine. I can rotate and pan and comment and communicate, even explode and measure components of the design. The other thing that I can do is I can comment on and see any previous comments. I can share the design with others who can contribute and provide feedback. I can do a real-time review, which is called live review, and I can export the file in a number of different formats from here. If we have a quick look at the share capabilities, you'll see here that I'm given a password. There'd be a password there where I can copy that and send that through to, via email. I can automate that process of sending that information through to someone by putting in their email address there, even turning on the likes of password requirements. And I can even copy and paste shortcode into my website that would embed the 3D model into my web page. And furthermore to this, I can even edit in the browser. Now this is using a preview technology, which is Fusion 360 that's running from within inside of a web browser, in this instance, like I said, Chrome, so again, no installation. Recognizing that what's happening here is it's loading the model up and giving me the ability to be able to make changes. Now in the preview release, as I understand it, this technology is limited to the ability to be able to modify the parts only. But having said that, I can still gain access to the assembly if need be, narrow down to the components that I need to make changes on, open those components up, and then go about making changes where necessary, even if I don't necessarily have Fusion installed on the machine that I'm potentially working from. So extremely powerful capabilities there, looking at the way that you can communicate on designs. Okay, so just in quick summary, why Fusion 360? Really it comes down to a number of key aspects. One system, one user interface. Here I was able to work across effectively almost the entire workflow, bar the ability to be able to scan the geometry in. But everything else I was able to do directly inside of Fusion. So working with the scan data, doing the detailed design, doing the simulation, exporting for 3D printing, all of that, renderings and animations for sales and marketing, all of that information, all of those workflows can be done directly inside of Fusion 360. So there's no need for multiple products or applications. Furthermore, I can work anywhere. So it didn't really matter whether I was out of the office away from my machine, or potentially whether I needed to access the data from someone else's machine, and not necessarily a Windows machine. It could be a Windows or Mac, or it could be a tablet or a phone. I can still access and in some cases modify the geometry no matter where I am or what I'm trying to use. And like I said, one of the other key abilities was the ability to be able to collaborate with anyone. And this comes back to the fact that the design, much of the design was being done here in Melbourne. A lot of the manufacture was being done in Toowoomba in Queensland. And the testing of that and a lot of the feedback that we're gaining during that process was being done from Sydney. So across all of these locations, the information was being shared in real time. Everyone had access to the latest versions of the files, could make changes and track all and manage all of that change management process. So in quick summary, I think, and we've had conversations with Ed about this, we're really wrapped with this project and the outcomes that we've been able to achieve. We really think that this has been a success. So, and if you look back at the objectives that we had with the project, we definitely believe that a lot of those objectives have not only been met, but exceeded with the result that we've been able to get from this project. So it didn't matter whether it came down from fit, which was really good using the workflow that we've done, to the weight of the design, to ease of use, down to the the manufacturing process, or even the cost, which is significantly less than equivalent prosthetics that are available on the market. We believe that in many respects this has really exceeded our expectation. How can you gain access to this type of technology? Well, quite easily. You can just do a quick search in Google for Fusion 360. I'd be looking for something like the trial page. If you're wanting to download and have a little bit of a try and understand the workflows, some of the workflows that we've talked about here, you just simply put your details in there and you can download the free trial. If you're wanting to understand a little bit of the capabilities between the two variants of Fusion 360, there's a really good table here under the compare option that shows you the capabilities of each of those. Realistically, the difference comes down to the simulation and manufacturing capabilities, which the ultimate variant has more of. Finally, I just want to say thank you to, firstly for you to attend this webinar, but I also want to extend a thank you to Ed, Nora and Millie for being such wonderful participants in this program. It really has been an honour to work with them and support them through this process, and I'm glad that we've been able to achieve the result that we have. Also want to thank the team at A2K, in particular Karen and Adrian, who came on board with this project very early on, were all for it, really brought the project to us, and we're enthusiastic through the entire process in trying to collaborate and bring together people to make this as successful as possible. And finally, it would definitely not been possible without the help from Stephen at Reality 3D Printing, who was always willing and able to make parts for us to test and showcase as part of that process. So thanks again to everyone involved in this process. Finally as well, some Autodesk people. The team here have really helped out. The Kilsyth team, Russell and Paul, that were able to get the scanning done. Ali, who helped me out with some of the freeform surfacing, and Pinchin, that was really helping to bring some awareness to the project. I really appreciate it. If you're after some more information about this, please, or Fusion 360 or this project, firstly, your reseller is going to have a lot of information about Fusion 360. If you're trying to find your lead reseller in your area, please do so at autodesk.com/resellers. You can find further information specific to Fusion 360 at the link shown on the screen. If you'd like to reach out to me about some of the specifics or further information about this project, feel free to do so. My contact details are on the screen and available for you there. Otherwise, I just want to say thank you for attending today's webinar. I really appreciate you coming. Remember, we've got a series of further webinars looking at some other things through the remainder of summer. But for now, thank you for attending. Have a good day and hopefully see you next time.